the last in our discussion about inverse trigonometric functions. And in this video, we're going to talk about what it means to compose functions that are inverse trig functions with regular trig functions. So what does it mean to compose? Well, it doesn't mean to compose music. But the word compose means kind of put something together. Well, it's definitely not decomposing. But we will want to be able to take apart the thoughts that are put together. Here's an example of an exercise where we are composing a trigonometric inverse function with a trig function. And we want to think about this step by step because we want to pull apart the two concepts that are happening here. The first thing we're going to think about is, what does this mean? Cosine inverse, remember, that means I'm looking for an angle measure. And remember that that is going to be defined only between 0 and pi. And we're looking for an angle measure that has a cosine that is the same as cosine of 7 pi over 6. Okay, well, let's first find cosine of 7 pi over 6. Well, to do that, we would go to the unit circle here, find 7 pi over 6, and I shaded it here so you could kind of see it. We pull the x value. And so the x value is negative 3 pi over 2, the x value of the coordinate. And so I'm looking for something in the top half of the unit circle that's going to have that same x value by going directly above until I see that x value. All right. And so I'd be thinking about this angle here, 5 pi over 6. Now notice that this question is not actually asking for the cosine, it's asking for the angle measure in that top half that has the same cosine. And so we want to just talk about the location there. And it's important that we kind of see how reference angles come into play here. All right, so look at this first angle measure that we're looking at. The reference angle here is pi over 6, right? It's pi over 6 past pi. And so in order to find something that is defined for cosine inverse, it would be up here in that second quadrant, but it would have the same reference angle. So instead of adding pi over 6 to pi to get 7 pi over 6, we would be subtracting pi over 6 from pi to get 5 pi over 6. And so that is how we are going to use our unit circle and the visualization of it to get our answer. Because often we have examples that don't fall in the realm of what we are normally used to using on our unit circle. So let's take a look at this example. We are interested in the tangent inverse. So what angle measure on that restricted range, negative pi over 2 to pi over 2, has a tangent that's the same as the tangent of 10 pi over 11. Okay, so notice 10 pi over 11 is not on here. But I know by looking at this fraction, 10 over 11, that's almost 1. So it's going to be really close to 1 pi. Okay, so something along this line. Okay, so notice I don't know what the tangent is there, but I don't need to. All I really need to know is, what angle measure in this restricted range, negative pi over 2 to pi over 2, has the same tangent as 10 pi over 11. Okay, so think about what we know about the tangent here. We know the tangent is going to be negative, and so we know that it's going to end up in not the first quadrant, but the second quadrant, because the tangent is negative in second quadrant. So it's going to look like this. All right, and then we want to think about how reference angles come into play here. So remember, for this first angle measure of 10 pi over 11, we would find a reference angle for this and then apply it over here, okay? So what is the reference angle? What is the angle formed by the x-axis and the terminal side of this angle? And if this is 10 pi over 11, what we're really thinking about is how much further do I have to go to reach pi? And that would be pi over 11. So I want to use that same reference angle over here. And remember that all of these angle measures we're going to refer to as negative angle measures. And so I can say that what I'm looking for is something with a reference angle of pi over 11 going in the negative direction. And so we can go ahead and say that that is going to be negative pi over 11. All right, now this last example, we've got a sine inverse of sine of 4 pi over 5. So that first part is going to tell us where we're looking, right? Where is sine inverse defined? Do you remember? That is defined on the right-hand side of the unit circle. So from negative pi over 2 to pi over 2. So that on the right-hand side is where I'm going to be looking for my answer. Okay, and so what I'm really looking for is an angle measure between negative pi over 2 and pi over 2 that has a sign that's the same as the sine of 4 pi over 5. Okay, so let's look at 4 pi over 5. Where would that be? Well, again, we want to think about 4/5 of pi. So pretty darn close to 1, but not going over, something like this. All right, after I identify that 4 pi over 5, what angle would have the same sign or the same y value? Okay, so it would have to have the same y value, but it's going to be on the right-hand side. So we can go just directly across and create a triangle directly across. All right, and now we're going to use our reference angles to identify what is that angle measure. Okay, so if this orange angle has a measure of 4 pi over 5, then the reference angle is going to be pi over 5. All right, so that means that my reference angle for the purple must be pi over 5 as well. And what do we know about all angles in the first quadrant? They are their own reference angle. So our answer here will just be pi over 5. Okay, so in all of these cases, we have been composing an inverse trig function with a trig function that's the same function but not an inverse. So in these next examples, we see that the composition is a bit different. The inner function is the inverse, and the outer function is just the regular trig function. Okay? And so we handle this a little bit different because we're going to reverse our thinking and we're going to draw a sketch. Okay? So let's think about what this is saying. This is saying, what is the cosine of an angle that has a sine of 3/5? Okay? And so we are going to look at the sine inverse of 3/5, which we know is only defined from negative pi over 2 to pi over 2. So that's going to be first quadrant. So once you've drawn that triangle, then we're going to label it appropriately because we know that this angle that we've drawn is going to have a sine of 3/5, which means the opposite side will be 3 and the hypotenuse will be 5. Then I can use the Pythagorean theorem to solve for the side that I don't know. Okay, so once I do that, I know that 3 squared plus whatever I'm missing, that x squared, is equal to 5 squared. X squared is equal to 16, and then in this case, x would be 4. So I can label my triangle 4, and now I've got it labeled so that I can find the cosine. What is the cosine of that angle? Well, that will be 4 over 5. So that's how easy this process is. It's a little easier to do for most students than the other one. All right, how about this one? Find the cotangent of sine inverse of 2 rad 13 over 13. All right, so this is really saying find the cotangent of an angle theta that has a sine of 2 rad 13 over 13. So we're going to go ahead and draw our triangle in that first quadrant because the y is positive here, right? We know this is going to be in the first quadrant, so we're going to draw it that way. And then we're going to label it appropriately. This angle that we've drawn has a sine of 2 rad 13 over 13. So I'm going to label the appropriate sides. The opposite side to theta will be 2 rad 13, and the hypotenuse will be 13. And then, again, I'll use my Pythagorean theorem to solve for my missing side. 2 rad 13 squared plus x squared is equal to 13 squared. So when I square that 2 rad 13, that would be 2 squared times the square root of 13 squared, which is just 13, so 4 times 13. And I would end up with x squared is equal to 117. And that means that x is going to be the square root of 117, which does simplify to 3 rad 13. Okay, so let's go ahead and put that where it belongs. Now I'm looking for the cotangent of theta. Okay, so the cotangent of theta will be adjacent over opposite. My adjacent side there is going to be 3 rad 13, and my opposite side there will be 2 rad 13. And then I would simplify that to just 3/2. All right, the last of these examples is similar to the rest. We are looking for a cosine of an angle that has a tangent of 5/4. So we draw an angle in the first quadrant that has a tangent of 5/4. So we're going to label this with an opposite side of 5 and an adjacent side of 4. Now notice my triangle is not drawn to scale because obviously the bottom side is longer than that right-hand side. But it doesn't really matter because that sketch is just showing us what is happening. I've got 2 sides and a hypotenuse. So I can use the Pythagorean theorem again to solve for my radius, right? This hypotenuse. Okay, so 16 plus 25 would get us r squared is equal to 41. And so r would equal the square root of 41. So now we can determine the cosine. The cosine of theta would be 4 divided by the square root of 41, which then we would rationalize to 4 square root of 41 over 41. Okay, we have got one more type of problem to look at with composing inverse trig functions. And that is very similar to what we were doing here, except we just have some algebraic expressions instead. Well, the technique will be exactly the same. We will just need to label it with these algebraic expressions and then solve in terms of x. So let's go ahead and try. We want to find a sine of an angle, theta, that has a tangent of x, which we could call x over 1. We know that this angle has a tangent of x, which means we can express that as x over 1. So that means my opposite side will be x, and my adjacent side will be 1. And then I can use my Pythagorean theorem and solve for my radius. So we know that 1 squared plus x squared will equal r squared. And then if I take the square root of that entire quantity, then I'll know my radius. So r would equal the square root of 1 plus x squared. So we'll put that there. Now I'm going to identify the sine of that angle. The sine is opposite over hypotenuse, so we would say that's x over the square root of 1 plus x squared. And then when we rationalize that expression, we will get x times the square root of 1 plus x squared all over 1 plus x squared. All right, the next example we are going to look at, we're going to be finding the cotangent of an angle that has a sine of the square root of x squared minus 9 all over x. So let's draw our triangle. And let's label it appropriately. Our opposite side will be the square root of x squared minus 9. Our hypotenuse would be x. And then we would use Pythagorean theorem to solve for our remaining side. So we're going to square this square root of x squared minus 9, and we're going to add it to the square of our variable. We'll just call that s for side. And we'll set that equal to x squared. Now when I square this quantity here, I'll just get x squared minus 9. And when I subtract this x squared, I would just get minus 9 plus side squared is equal to 0. So s squared would equal 9, and that means our side there would be 3. So I'll go ahead and label and then write our cotangent. Remember, cotangent is adjacent over opposite, or 3 over the square root of x squared minus 9. And then we would rationalize that denominator. 3 times the square root of x squared minus 9 all over x squared minus 9. Now our last example, we're going to find the cosine of an angle, theta, that has a sine of 1 over x. and we can draw that triangle in our first quadrant. With this angle, we're going to have an opposite side of 1 and a hypotenuse of x. And then we would go ahead and use our Pythagorean theorem to solve for that side. So s squared plus 1 squared is going to equal x squared. Now I would subtract the 1 to the other side, and I'd have s squared is equal to x squared minus 1. Take the square root, and s would be the square root of x squared minus 1. Now our cosine is going to be the adjacent side over the hypotenuse, and so we just get the square root of x squared minus 1 all over x. Well, that wraps it up for inverse trig functions. I will see you next time.